Mass spectrometry is a powerful analytical technique used to identify the chemical composition of a sample. By converting molecules into ions, we can manipulate them using electromagnetic fields to reveal their unique atomic signatures and isotopic ratios. Isotopes are atoms of the same element with different numbers of neutrons. Because they are chemically identical, we cannot separate them using reactions. Instead, we must rely on physics to sort them based on their physical mass. The process follows three distinct stages. First, we turn the sample into charged particles. Next, we give them kinetic energy. Finally, we use a magnetic field to bend their paths, sorting them by their mass-to-charge ratio. In the ionization chamber, high-energy electrons collide with the sample, knocking off electrons to create positive ions. This charge is essential because neutral atoms cannot be influenced by electric or magnetic fields. The positive ions are repelled by a positive plate and attracted toward a negative grid. This electric field accelerates all ions, giving them a specific amount of kinetic energy determined by their charge and the voltage applied. As ions enter the magnetic field, they experience a perpendicular force. This force acts as a centripetal force, causing the ions to travel in a circular path. The radius of this path depends on the ion's momentum. By combining the equations for kinetic energy and magnetic force, we find that the mass-to-charge ratio is proportional to the square of the radius. This means heavier ions swing wider, while lighter ions curve more sharply. Think of it like a car turn. A light sports car can take a sharp turn easily, while a heavy truck tends to plow straight ahead. In the spectrometer, the heavier isotopes have more inertia and resist the magnetic pull. At the end of the curve, a detector records the position and quantity of arriving ions. Each hit generates a small electric current, which the computer translates into a peak on a mass spectrum graph. Let's look at carbon-12 and carbon-13. Though they differ by only one neutron, the magnetic field is precise enough to separate their landing positions on the detector by several millimeters. First, we calculate the velocity. Using the acceleration voltage, we find that the ions are traveling at incredible speeds, over 100,000 meters per second, before they even enter the magnet. Next, we calculate the radius. Because carbon-13 is slightly heavier, its radius of curvature is larger. This physical displacement allows the detector to distinguish between the two isotopes clearly. The resulting mass spectrum shows the relative abundance of each isotope. For carbon, the large peak at 12 and the tiny peak at 13 reflect the natural distribution of these atoms in our world. Some elements, like chlorine, have very distinct isotopic signatures. Seeing two peaks in a 3:1 ratio at masses 35 and 37 is a smoking gun for the presence of chlorine in a molecule. To summarize, mass spectrometry uses ionization to make molecules visible to fields, acceleration to give them speed, and magnetic deflection to sort them based on their physical mass and inertia. Let's test your understanding. If we increase the strength of the magnetic field, will the radius of the ion's path increase or decrease? Think about how a stronger force affects the curve. The answer is decrease. A stronger magnetic field exerts a greater force, pulling the ion into a tighter, smaller circle. This principle is used to tune spectrometers for different mass ranges. From identifying pollutants in water to analyzing soil on Mars, mass spectrometry is an essential tool of modern science. By applying simple laws of physics, we can unlock the secrets of the atomic world. Generated by Vision Solve AI.